Okay, so let's think classically about this for a little bit. Okay, so the energy of our wave, right? This is what Maxwell tells us is proportional to the amplitude of the wave. And what do we observe when we shine light at this? Well, if you shine light with a sufficient amount of energy, when you shine with a sufficient amount of energy, it kicks electrons off. So when you shine light, electrons come out of the metal. Okay? So this is kind of, in some ways, this is kind of how like a solar cell works. A solar cell is just basically a lattice of metal. It's more complicated than that, but you can think of it like that. And you shine light at it, and it excites an electron, which causes a current to be formed in your material. That current is then transformed into is used to charge a battery, right? And then you can therefore create energy with this motion, right? So you can convert light energy into electron kinetic energy, if you will, right? The light comes out as a wave with some amplitude, and the electron comes out like a particle with some kinetic energy. All right, so let's think about this classically. All right, so if I were to say plot if I were to say I was going to plot the frequency of the light. Now I'm going to use frequency here. So let me just remind you again that the wavelength of a wave is equal to c over its frequency. Right? I'm always going to use this kind of squiggly v for frequency. And the units of frequency are in per second. Right? That's how fast in time a wave goes from through a period. And of course, lambda is the wavelength, which is in meters. Right? And light always travels at c, so you can interconvert with this formula. Okay? So what that means is that the longer the wavelength, right, the bigger the wavelength, the shorter the frequency, the smaller the frequency, as you would imagine. Okay? That's a pretty common observation. So a short wavelength, of course, which is very blue or ultraviolet, corresponds to a very high frequency. Okay, so what I'm going to do now is plot frequency versus the number of electrons, the current, if you will, that's created by this light, right? The current. So I'm just going to call it number of electrons, which is current. All right, so what do we expect? So let's imagine that we set our light to some frequency V naught that's sufficiently high. And what we'll see is that what we expect is that as we increase the frequency, you put a little more energy into the system, right, and you get something that maybe looks like this. Okay? So let's say this is just like a normal brightness. So let's say this is the amplitude of this wave is small. All right, so it's a dim light. Okay. And we notice that this is what we think. So like you don't have any signal because you don't have enough energy to kick that electron out, and then you have enough, and then as you increase the frequency of your light, you get more electrons out up to a certain point. You're driving it harder and harder. Now the question is, what if we make the light bright? All right, what if we brighten it, keep everything the same, but we increase the brightness? All right, well, if we think about it classically, we're kicking electrons off with kinetic energy. Right, so think of this light as a baseball bat. All right, and the energy of our baseball bat is the amplitude squared, right, which is the brightness. Right, so as you turn the brightness up, you would say, okay, our light baseball bat, we're swinging harder and harder and harder against this metal, so we should kick the electrons off harder and harder. And so what you would expect is that as you start to increase the brightness, that the critical frequency that the light gets off is lower because you have more energy per light wave, because your amplitude is larger, you have more energy per wave. If you think about it, if you think about every trough that hits or every peak of the wave that hits the electrons, the trough is larger, so you're imparting more energy into it every second. And you would imagine that a bright one will generate more electrons and at lower frequency than a bright one, or than a dim one, right? Because you're putting more energy into the system, right? So this is what we expect classically. And that's a totally reasonable assumption to make. Right? We know that blue light, right? You can think about it in terms of like cancer, right? Microwave radiation, despite what people tell you, radio radiation, which is short frequencies or long wavelengths, doesn't have any effect on your body. But ultraviolet light, which is short wavelength, really high frequency, imparts a lot of energy, right? It can cause cancer, right? It can cause chemical reactions. So there must be some association with frequency and energy. We know that blue light's more dangerous to us than red light. It has something to do with energy. So this seems like a reasonable assumption to make. This is what's going to happen. The brighter the light is, the harder you swing the bat. So let me show you what you actually get, though. Not surprisingly, this is not what you get. Here's the actual plot. So here's my V naught. And at some brightness, I'll do it in purple again. I see this curve. Dim. And then when I impart the bright light, I get more electrons out, but the frequency doesn't shift. The critical frequency is still the same. The frequency is independent of the intensity. All right? So if my light is red enough that it doesn't excite the electrons, I don't see any electrons out, and then there's a point at which the electrons have enough energy to move, and I immediately see a current. And of course, if it's brighter, I see more electrons, but it doesn't change where the electrons start to get kicked off. What does that mean? Well, that means that the energy imparted by the amplitude of the wave really isn't really imparting any energy into the electron. What's imparting energy into the electron is the frequency of the wave. Right? Because regardless of the brightness, the electrons don't appear until a very specific number. Okay, so the frequency ultimately determines how much energy you need to kick an electron off. And the brightness only determines how many electrons you get. So what does that mean? That means that the energy of the electron is proportional to the frequency, and the number of electrons is proportional to a squared. All right, so here's an interesting, I'll give you guys a second to catch up. Here's an interesting experiment. Now what I'm going to do is I'm going to monitor how much, when the electrons are ejected, how much kinetic energy they have. All right, so I'm going to turn my light from red to blue. I'm going to sweep my light over my sample, and I'm going to measure how much residual kinetic energy there is as a function of frequency. Instead of the number of electrons, I want to measure the energy of the electron instead. And let me save this in case it crashes. All right, so now what I'm going to do is I'm going to plot frequency. Oh, that's not. Stroke recognizer. Plot frequency versus the kinetic energy of the electrons that are emitted. Remember that kinetic energy is 1/2 mv squared. Right, so all electrons have the same mass, so it's proportional to the velocity, how fast they move. Not surprisingly, we don't see any motion of electrons below V naught, right? Because they don't have enough energy to leave, so they have no kinetic energy. And what you observe is that as you increase the energy, as you increase frequency, the energy increases linearly. In fact, I'll draw it as a straight line, instead of a half drawn one. Like that. So as you increase the frequency, the kinetic energy of the electron goes linearly with the frequency. Well, that tells you exactly the relationship, the function between frequency and energy. It's linear. All right, so what does that mean? It says that the energy of the electron is equal to some proportionality constant, the slope of the line, h, times the frequency. This is what I would call our zeroth postulate. It's not our first one because it's not really a postulate, it's an observation. But it's so important in this class, this equation, that I'm going to call it a postulate. It's called Planck's law. And what does this say? It says that the energy of a particle, or any energy, it's in joules, is somehow proportional to a frequency. Right? If you have an energy for your particle, it also has a frequency associated with it. Completely universal. Now here's the interesting thing about this, right? How did we measure this energy? Well, we measured it like a particle, right? We measured a particle of a mass with a velocity, right? We measured how long it takes to travel a meter. That tells us the kinetic energy of it, right? So the electron is being detected as a particle, but what this says is that it's proportional to frequency, right? So there's some wave characteristic on this electron, right? This frequency is a wave property, and this is a particle property, energy. Right? So what that means is that the electron, we can observe it like a particle with kinetic energy, but we can also observe it like a wave. It has an associated frequency with it. And there's some proportionality constant between these two. Right? This constant is perhaps the most important number in this class. It has a very specific number and a name. This is what's called Planck's constant, the Planck constant. Planck's constant. And it's called H, so I called it H. And it has a fixed value now in SI. It's fixed to a specific number, doesn't have an uncertainty. It's 6.626. Let me write the whole thing. That's usually how I round it down, but I'll add some numbers to it for the complete precision. So here's the mantissa, 6.6260715 times, sorry, I'm keep clicking it, times 10 to the minus 34 joule seconds. All right, so let's look at those units really quickly. Joule seconds, that's a strange unit. We'll have to think about those units later. They actually have a meaning. But let's say this is joule seconds, and frequency is in per second, second to the minus 1. So this combination gives you joules. Okay? So this is a fundamental relationship that converts us between energy, again a property of everything, and frequency of a wave. Right? Or light. Right? You can think of this, if we're instead of electrons, think of this as a light particle with a wave, right? A light wave. But a light, as we know, light can also be a photon, which is a particle. And the energy of that photon is h times the frequency of the light. All right? So every photon that has a frequency, a non-zero frequency, has some associated energy with it. And that's also true for electrons, right? I just showed it. Electrons show the same property, right? Every quantum mechanical object satisfies this. It has an associated, anything that has an energy to it also has an associated frequency with it. How can we take this a little further now? So, we have E equals h nu. Right? Particles have energy, like a particle, objects have particle behavior, energy, and frequency, like a wave. Well, remember that we can also convert frequency to wavelength. Right, so that means that, of course, E is equal to hc over lambda. That's another way to write this. Right? Again, wave and energy properties, particle properties. But electromagnetism and EM physics, I'm not sure if you guys learned this, but we'll just write it down for a second, states that the energy of a light wave or some sort of light field, the energy of that field is equal to C times the momentum. Sorry, that looks like density. The momentum. This is momentum of the wavefront, right? So you can think about the wave is moving through space at some velocity. It has some momentum. And so when you combine all of these things together, you get that the momentum of any quantum mechanical system is h over its wavelength. So this is the momentum of a wave, of a quantum mechanical wave or particle, right? And its momentum is associated with lambda, its wavelength. So what does that mean? Well, that means the longer, sorry, let me start over again. The shorter the wavelength, right, which would mean more blue, the higher its momentum, right? The smaller the wavelength, the larger the momentum. It's really, really fascinating. You can prove that this works. What does this imply? Well, it implies that if you had a single light particle, just one photon, it has a momentum to it, in the sense that when it hits something, it imparts a force. And the force that it imparts is proportional to 1 over its wavelength. So imagine you have a molecule floating in space by itself, not doing anything, and it absorbs a photon. All right? And it absorbs that photon, it will accept that momentum because of conservation of momentum. The photon has some momentum, it's imparted into the molecule, and then the molecule will now have momentum. So light imparts a physical force against the molecule. Right? And every particle, everything has this property, including all of you. It's not hard to calculate this. Imagine that your momentum is me with 100 kilogram fat boy walking 1 meter per second. I can calculate the momentum of that. Remember, momentum is mass times velocity. 100 times 1, I can calculate my wavelength, right? I just take h over the my momentum. Now, this number is, for me, 100 kilograms, and I'm moving 1 meter per second, right? This number is on the order of 100. This is 10 to the minus 34, so this wavelength is really, really small, right? That's why I can't see my own wavelength, right? That's why I look like a particle, because my wavelength is microscopic compared to my physical size. Right? The wavelength here is on the order of 10 to the minus 36, 10 to the minus 36, right? Meters, right? So you can't observe my wavelength, right? I'm a pure particle because my wave properties are basically negligible. But what if you take the momentum of a hydrogen atom moving, let's say, a helium atom, which is only 4 AMU, very, very small mass, right? 10 to the minus 26 kilograms, roughly. Now the wavelength is actually pretty long. In fact, if you get a helium atom cold enough, really any atom, cold enough, which means its momentum is slow, because if it's cold, it's not moving very fast. The wavelength of the helium atom is actually longer than the actual size of the system, right? So if I draw a helium atom, it looks this big, and then I calculate its wavelength, right? And so there's a cosine wave associated with this particle, of this momentum, and the length of the wave is larger than the helium atom, right? Here's the wave associated with that helium atom. The wavelength. And so, in fact, the helium atom doesn't act like it's a little ball. It acts more like a wave, because the wavelength is the larger scale. And the wave properties of helium become more significant than the particle properties of helium at low temperature. And so helium at low temperature, say around 3 or 4 Kelvin, you can't treat helium like a ball. You have to treat it like a distributed wave that's distributed over space. with some wavelength. And that's one of the reasons why cold helium becomes what's called a superfluid. This is why it has that phase transition, because it gets to the point where the distance between two helium atoms is small enough that the wavelength of one atom is larger than the distance between the two helium atoms. So here's if you think of this as the wave for the helium atom, for one helium atom, for this helium atom in particular, and I put another helium atom in here, right? This is the average distance between two heliums and liquid helium, but the wavelength of one particle extends past the other one, right? So there's no way to know physically where one atom begins and one ends, right? Because let me draw the wavelength for the blue one, the wave for the blue one. It also has the same wavelength, right? And they add together. So they're not really two balls. The way to treat two helium atoms at cold temperature is not two balls, but rather two waves, right? They have wave-like properties. And this is and it turns out that if you take this to the logical maximum, where you have this giant material, thousands of helium atoms are all delocalized, that they're not balls that are an angstrom wide, but rather waves that are 5 to 10 angstroms long, then all of the atoms blur together. There's no distinction between one atom or another. They're all overlapping each other. And helium has this very unique property. It causes it to become something called a superfluid at low temperature, where all of the waves of all the little atoms, they all add up collectively to make one giant wave that represents N helium atoms. And that's a superfluid. Right? Where the wave properties win out over the particle properties. Right? So this is universal, completely and utterly universal. It's just that, and this also tells you where quantum mechanic behavior becomes important and not. If me, I'm about, I don't know what I am, like 25 inches this way. If my wavelength is 10 to the minus 34 inches, my wavelength is much smaller than the extent of my body. I act like a particle, right? But if I'm in a regime where the size of my particle is on the same scale of its wavelength, or smaller, then that's where quantum mechanics really starts to kick in, because you can't really tell whether it's a particle or a wave. Or if the length scales are about the same, it's both, right? It has some wave properties and some particle properties. So this relationship kind of gives you a sense of where quantum mechanics becomes important and where it isn't. Where it isn't is where the wavelength is tiny compared to the length scale of your system, and it's important where they're competitive, or the wave is even more important, or even larger. Right, so this is a universal concept. This is wave-particle duality, right? That every particle has an associated frequency, which is proportional to its energy, and an also associated wavelength, which has something to do with its energy as well. So particles that are very low energy, they have very large wavelengths, and particles of very high energy, they have very narrow wavelengths. Okay. So that's when I want to talk about wave-particle duality. So that's my third principle. So we have a couple of things. Our particles act like waves in the fact that they have superposition. We can add them together and subtract them together. You can have a white plus black, a white minus black electron. That's what your homework explores. We know that they're quantized in the sense that their properties can only take discrete values. In the sense that there are a specific set of energy levels that a system can exist in, right? That's why we have spectra, these line spectra for our atoms. And we have wave-particle duality, right? Particles are both waves and particles at the same time. They exhibit both characteristics. And so all of these things were measured and known before the theory was implemented. That's why I introduced them first, because these are the kinds of problems that physicists had to solve in the early 20th century. Like, these are the things facing them. And so they have to come up with a set of statements that explain the results. And so we're going to look at two approaches. In fact, you've looked at one of them in your homework, the matrix approach, which was developed by a man named Werner Heisenberg, the namesake of our favorite chemistry meth dealer from television. He comes up with this concept of matrices and vectors. And then there's another man who I think will spend a lot more time on his approach. His name is Erwin Schrödinger. He's a Swiss physicist. He comes up with this idea of what's called a wave function. He uses wave theory Right? So he thinks about electrons and things as waves and uses the physics of waves to start thinking about how particles, the physics of particles using the wave approach. And they both have advantages and disadvantages. It turns out they're equivalent. They give you the same answers, but again, they're two different perspectives on the same problem. And we'll see that a lot, that there's duality between two things, that two things can be true simultaneously, but at the same time they're not. You can switch between them. You can only have one or the other, but you can switch. Just like color and flavor. And so Schrodinger uses this wave approach. He thinks about the physics of waves and light and electromagnetism to tackle this, because he sees that these particles have wave properties, so that must say something about their physics. All right, so Schrodinger in some ways is a very conservative physicist. He takes theory from the 1800s, right, the theory of waves and electromagnetism, and beefs it up a little bit for this microscopic system. All right, so he takes old physics and revitalizes it. Heisenberg, with his matrices and vectors, creates an entire new language that no one understood at the time. In fact, most people didn't think that Heisenberg was full of shit. That he was just like an insane man, and these were just his absurd writings and thoughts that didn't make any sense. But it turns out he was right the whole time. He just was looking at it from a completely different, more abstract world than Schrodinger. So Heisenberg is a very modern approach. He uses physics and math that at the time very few people understood. Nowadays, if you're an engineer or something, you take linear algebra, you learn about vectors and matrices. You learn about this stuff in undergraduate. But in 1910, very few people understood matrices and vectors. Very few, especially in physics. And so Heisenberg uses this new modern math to explain something. It's a much more abstract way. It's very, very, very powerful. And Schrodinger uses more of a physical approach, more conservative approach. And what we'll find is that Schrodinger's approach is very, very useful for conceptualization. We'll find that it's not very useful for calculation when you get to complicated problems, but for understanding how quantum mechanics works and how, say, an electron orbits a proton in a hydrogen atom, Schrodinger's wave method is incredibly useful. So what we'll do is we'll focus on that wave approach. We'll take this idea of wave-particle duality and take it to its logical maximum. And we'll come to points in our calculations where we'll be like, this is not the most efficient way to do this. And then we'll come back to Heisenberg's matrices and vectors, and we'll see that Heisenberg actually provides us very unique advantages for calculation. But I think it's important to think about both perspectives because they're both useful in their own ways. Okay, so we're not going to get through many postulates today, but we'll get through the most important one. Postulate 1. This is the wave function postulate. All right? I'm sure you've heard of a wave function before, maybe in passing, maybe in a textbook. Here we're going to define what a wave function is. And we'll be able to, without doing very much math, a wave function is going to have certain properties. And with these properties, we can actually come up with a very toy model for a wave function, and we can see how it works. All right, so a system, a quantum mechanical system or state. So anytime I write QM, that means quantum mechanical or quantum mechanics, so I'm just to save me space. A quantum mechanical state or a system, could be a particle, could be an energy level of hydrogen, whatever, is completely, the important thing here is completely specified. Which means is that the only thing we need to know about the system is this object, the wave function. It's completely specified by its wave function. Which is a function. It takes some variables in and spits a number out. Okay? And the label that I use for wave functions is psi. The Greek letter psi. It looks like a pitchfork. All right, so anytime you see psi, think wave function. All right, and it takes some variables in. All right, so we have to think about what variables our wave function takes in. Well, we have lots of choices, it turns out. But we could take a very logical set of variables. So for instance, let's think about an electron orbiting, let's say an electron in a box moving around. Right? What are some coordinates? What are some variables that we can track our electron? Well, the position of it, right? So why not we take this wave function and put in its input is the position of the system, which I'll write as r vector, right? That's a three-dimensional vector. I don't know if it's 1D or 2D or 3D, but it's some position. I'll write that out in a second. And we also want to think about how it evolves in time, right? Because we might put a particle at one spot, and we're curious what it does 10 seconds later. So a wave function takes in two values, the position, in this case, and the time. Okay? And where r is a position vector in three-dimensional space. Right? So it's a three-dimensional vector. All right, we'll go to situations that are 1D eventually, because 3 dimensions is hard to work with sometimes. Often we'll do things in 1 dimension. Find simplifications. But in general, it's dependent on all 4 coordinates of the universe, which is space, 3 dimensions, and time, 1. Okay, and wave functions satisfy specific properties. Okay, so the first property that it satisfies is called the probabilistic property. The wave function is probabilistic. What does that mean? Well, the statement is that if we take the wave function and square it times a infinitesimally small volume, dx, dy, dz, all right, so we're taking the square of the function and we're looking at a very, very small spot, right? This is the probability. It corresponds to the probability, right? The chance of observing the system in volume dx, dy, dz. Okay, so imagine that we have a little, let's imagine we put our particle in a 3-dimensional box. All right, it's an electron sitting in a box. And we take a little chunk of the box, a little sphere of the box, all right? And what this says is that the probability of observing the electron in that little box is psi squared. Okay, so we square it. The square of the wave function gives us a probability. All right, and what does this imply? Well, it says that the total, probability, now let's think about the question, what is the total probability of finding a particle anywhere in the box? Right, so how would we calculate that? All right, the total probability, so the probability of finding the electron anywhere is going to be the integral of this probability. So we're going to integrate over the box or space or whatever of psi squared dx, dy, dz. Okay, so we're going to integrate that function over the entire box, right? And that'll give us the probability of finding the particle anywhere. Well, the answer for that should be 100%, right? If the particle's in the box, then there's a 100% chance of finding it anywhere. So probability runs from 0 to 1. Chance runs from 0% to 100%. Probability is chance divided by 100%. So it runs from 0 to 1. So what should this be? This should be 1. Let me write that as, that's a 1, by the way, not a 2. Let me write that as a 2.
Yeah, I was also going to say that about
psi
looks like a 4.
The psi looks like a 4. Oh, yeah, so I will often write psi with this little lazy little curve there. So I'm sorry, I'll do my best.
Yeah.
You'll get used to it.
I knew it was psi, just wanted to make sure in case anybody else was wondering if that was a 4
1.
too.
Okay. So this gives us a condition. So a proper wave function for our system, when you square it and you integrate it over the entire space of the system, it gives you a 1 back, right? Which implies that there's a 100% probability of finding the electron anywhere in the box, right? Now this is what we call a this is what we call our normalization condition. Right? And that any proper wave function, the integral of its squared has to be equal to 1. Okay? You may remember, if you've done the homework, you may think that the vectors for the electrons, they're all length 1. They have to be length 1. That was one of the properties that the electron vectors have. Exact same statement here. Right? Here, remember, if electrons, we're looking with the color, we're looking at a discrete space. They could be black or white. But here we're looking at electrons that are in position space instead of color space. And position can be a continuous number, right? Space is continuous. So you have to use an integral instead. Right? And it says that the integral of psi squared is equal to 1. This is the exact same statement as saying that the length of a vector, which is a wave function for our electrons in color space, the length of it is 1. It's the exact same statement. Right? Here we're moving from vectors to functions. So I've done that very kind of casually. Right? We'll have to come back to that. But that's the Schrodinger-Heisenberg difference. Schrodinger thinks about waves in space and time, and Heisenberg thinks about vectors in a space. And they're equivalent. So there's going to be every statement that I make about these functions, these wave functions, are also equivalent for vectors. There's an equivalent statement for vectors. There's two different approaches. Right? But this is the idea that the vectors have to be length 1. That the square, the length of the vector, represents its probability. And of course, the probability has to be 1. Right? So this is what's called the Born interpretation, the Born property, the Born interpretation. It's named after Max Born. That psi squared is the number that we actually interpret. Psi squared tells us things that we actually measure. We'll talk more about that as we go to it. But this is actually this psi squared idea is the key part of the Copenhagen interpretation, the psi squared. That when you integrate psi squared, you get 1. Right? This was a big controversy, and we'll see why later on why this is a problem, or why problems arise because of this, so weaknesses, if you will. But this is our assumption, the Born interpretation. Psi squared is a probability measure. It's going to, and that's why the wave function is so important. If we know psi squared, we know everything about the system probabilistically. We know the chance that an electron is going to be anywhere, and we can calculate exactly what the probability of it is being somewhere, whether it's going to be in the middle of the box, on the edges of the box, or floating in the middle. Right? This will teach us that. Or rather, it'll tell us that. So now what I want to do in my last 15 minutes is now think about, what does psi look like? What does the function look like? Right? Because the important thing is that when I square it and integrate it over all space, right, I'm going to have integrals maybe from 0 to infinity. That it converges to a number. Right? So if this integral comes out to infinity, say for instance, what if psi is a line? What if it's x? Right? What if it's psi of x is equal to x? Well, this integral would be x squared dx from 0 to infinity, and it would diverge. It would be infinite. So psi equals x, a wave function which is a line, is not a valid wave function. Right? This limits us that all physical systems have to be represented by a function that have a convergent indefinite integral. Right? That they're convergent in the space that you integrate them in. Right? So that really limits the kinds of functions we can use. Right? They can't just be polynomials. Everything's x squared and x cubed and stuff like that. That doesn't work here because they don't integrate to 1. So we have to think about what the structure of these wave functions look like. We already know something. We know that particles can be represented as waves. Right? That's what we learned from the photoelectric effect. Right? If a particle is a pure wave, then it must have a sinusoidal function associated with it. Okay, so let's think about that for a second. So let's think of this. So the first thing I want to say, I want to make a statement. We'll formalize this next class. This is called Heisenberg uncertainty. It's not the official statement of it, but We'll call it the naive Heisenberg uncertainty principle. Which is that if your knowledge of the position of a particle goes to 0, right? So this is localized particle, right? Like, so for instance, I can tell you that for certainty that the electron is sitting right here in front of Gabby, and it's right here. Okay, it's exactly at this point. So I have no error in the position of my knowledge of it. If this is true, then my knowledge of its momentum, right? How fast it's moving, what direction it's in, right? The wave properties of it goes to infinity. So the more I know about the particle's position, the less I know about its momentum, how it moves, and vice versa.
Is that supposed to be 0 delta x?
Delta x goes to, if delta x, your knowledge in delta x goes to 0, then the delta p, your knowledge in momentum, your error in momentum goes to infinity. And vice versa. So I'll just write that as well. If your knowledge and if your error in momentum goes to 0, then your knowledge in position goes to infinity. Right? So you can only know position and momentum. It's like color and flavor, right? If I know color exactly, I know nothing about its flavor and vice versa. Position and momentum work the same way. Right? This turns out to be wave-particle duality, just stated differently, and we'll explore that next class. So what I'm going to do is I'm going to define my state. I'm going to use this to my advantage. I'm going to pick one of these limits. So what I'm going to do is I'm going to define my wave function at a very specific momentum. All right, I'm going to know exactly how much momentum it has. And I'll say it has momentum p naught. And it's a function of x. We're not going to worry about time here. And we know that it's a wave. Right? We said that a particle with defined momentum is a defined wave, has a defined wavelength. And so let's guess, what would be a good sinusoidal function for this? Well, let's just do the most logical choice, which is we'll take an amplitude and we'll do a cosine function. And the wavelength is 2 pi over lambda, right? We wrote this down earlier, times x. And I can rewrite this as, with the relationship between momentum and, the relationship between momentum and wavelength, this comes out to be 2 pi p naught over h times x. Okay, so the wavelength of the frequency, if you will, of the wave has something to do with momentum. Okay, so this is the wavelength and the momentum are related to each other. All right, so this is a cosine of a fixed frequency. Right, so if I were to plot this wave on a coordinate system as a function of x, so x, and we're going to plot psi. It's just a cosine function, right? So it goes from a to minus a, and then back up, and then back down, and then back up, and back down, and so on and so forth. Right? So this is what the wave function of our electron of a defined momentum is. And you can see why it's delocalized. If you know the momentum exactly, which means it has one frequency, right? It's just a sine wave or cosine, you can see why it's delocalized in space. Why we don't know anything about the position. Because let's square this. Right? Remember, the probability of finding it in a region is the square of the wave function. So in purple, I'll plot psi squared, and all it is, again, what's psi squared here? Psi squared, in this case, is a squared cosine squared times 2 pi over lambda x. All right, we just square everything. That's easy. All right, and what's the square of a cosine look like? Well, it's an oscillating function that goes between 0 and the amplitude. So it looks like, so it peaks here and then goes down, and then goes up again, and goes down, and goes up again, and goes down. Like that. Okay, so this is so psi squared is the probability of finding the electron at a certain position in space. So what does psi squared tell us here? Well, it says that at this point and this point, this point, this point ad infinitum, that the probability is maximum, right? That the highest probability of finding the electron is where psi squared is largest, so that's here, here, right? It's at the peaks. But that also tells you that there are positions where the electron isn't present, right? The electron can be here, 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 and here, but not here, 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 because the probability is 0 there. But here's a contradiction. I said that if I localize the momentum, so I know the exact momentum that it's at, then my uncertainty in x is infinite. Well, what does that mean? Well, that means that the probability of observing the particle at any position is the same. I have no knowledge of its position, but this wave function, x squared, tells me that there are positions that are preferred over other ones. So that does not satisfy this property, right? Because I have some information about the position of this electron. I know that it's in half the regions it's visible, and half the regions it's not. So that doesn't satisfy my property. So what does that mean? Well, that means that this cannot be a proper wave function for my system. This is not satisfied. Right? No good. Right? Because what do I actually want? Right? So this is what this is my guess. Let me scroll down just a bit. What do I actually want? Well, again, I still want a sinusoidal wave function. Right? Because it's still a wave. Right? So I still want, I'll write psi in blue and psi squared in green here. And then what time is it here? Okay, we're almost done. Right? So I still want the same behavior in my space. I still want it to be a sine wave. But I want my probability to be the same at every point, right? I have no knowledge of where the electron is. So the probability should be a flat line. Right? There's no preference for it to be anywhere. Okay? So I need a function that gives me where psi is a sinusoidal function, oscillating function, but when I square it, I get a flat line. Right? There's only one kind of function that does this. There's only one acceptable function. All right, and I'll work out the math in just a second. So the only acceptable function here has to be complex. And the function is a to the I, let me erase this, 2 pi I p naught over h times x. It's this strange complex exponential. These are all in the exponent. So it's e to the 2 pi I p over h times x. We'll show that this gives me the right result. Now, why does this exponential function give me a sinusoidal function? Well, there's a beautiful theorem that says, let me find a space to write it. So I'll just write it here. This is called Euler's theorem, or Euler's formula. Which is that e to the ix is equal to cosine x plus I times sine x. Okay, so anytime you see an e to an exponent to an imaginary number, you can think sines and cosines. It's a complex number where the real part is a cosine and the imaginary part is a sine. Okay, so this has that sinusoidal property, but it's in the complex plane instead of the real plane. Right? There's a sinusoidal part and a cosine part, real and imaginary axes. Right? So there's two components. So what's the square of this function? So this is my last couple comments. Here, I'm going to do a new page, but I'll move it over so you can see. Okay, so this is my formula. So what I want to do is I want to square this function, right? And I should get a number, right? It doesn't have any sinusoidal properties. It's a flat line. So we should get a number out. So when you multiply, the rules of multiplying two complex numbers together, I'll come back to it. So the complex rule, which is that if you have a number y, which is equal to a complex number a plus bi, so if you have a complex number, a plus bi, then, let me change colors, y squared is equal to y, which we call the complex conjugate, which I give a star, times y. Sorry, I keep writing psi because I'm just so used to writing psi, sorry. This is called the complex conjugate. And a complex conjugate is where you take the imaginary part of the number and flip it by -1. So what this is equal to a minus bi times a plus bi. All right, so all a complex conjugate is the star symbol. This means I take the imaginary part and make it negative instead of positive. All this means is that if you think about motion in a circle, this is clockwise motion and the other one is counterclockwise motion on the complex plane. And when you do this math, again, it's not hard to FOIL this out. This is a squared plus b squared. Okay, so when you square a complex number, you get a real number out, just a number. All right, and it's the length of that vector. If you think about the vector AB, this is the length of that vector in complex space. All right, so what is psi squared here using this rule? Well, we're going to take the complex conjugate of psi and multiply it by psi. And again, all the complex conjugates, I take the I and make it negative I. So this is, I'll just do the math, it's a squared. There's two factors of a. E to the minus 2 pi I p naught over h times x times e to the 2 pi I p naught over h times x. Right, so psi gives, both values give me an a, so I get a squared. Here's the complex conjugate, right, minus I, and I have positive I here. These cancel out. Right, this is e to the minus, say, minus x times e to the x. Right, remember that, just a reminder, that e to the x times e to the y is e to the x plus y. Right, so the net exponential here is e to this minus this. So it cancels out. Oh, sorry, it's this minus this. Excuse me, it's probably a better way to look at it. This minus this. So you get a 2 pi I p naught over h times x in the component minus the same thing. So you get e to the 0 goes away. The complex part goes out. And so psi squared is just the amplitude squared. It's a number. Exactly what we want. Therefore, this is the big take-home message. Wave functions are complex valued. This is why I hate when people call them imaginary numbers, because they're not imaginary. They actually describe reality. Wave functions, and in fact, electromagnetic waves are too, they're complex value. You need to have, waves have a cosine part and a sine part. Any wave has an arbitrary cosine part and a sine part. And the way that we represent waves that oscillate in this sense, that have two components, we use imaginary numbers. We use complex numbers to do that. And because we're dealing with waves, right, we're treating our system like waves, our systems are going to be complex valued. They're going to have complex numbers. Now that sounds scary, but we're going to make choices as we go, because ultimately we're going to be dealing with real systems, right, real hydrogen atoms and stuff. We're going to be making choices. We can make choices so that we can get rid of the complex numbers. Right, but there are situations where they arise and we can't do anything about it. So just be prepared, there are going to be I's appearing, but we're going to do our best to get rid of them as much as possible, because we can't observe complex numbers. They are imaginary in the sense that we can't observe them. We don't see complex numbers. So we're going to try to come up with ways to project things onto a real axis so we can observe them. But ultimately, the physics are defined by complex numbers. So we need to deal with them. All right? So that's where we're at right now. That's our wave functions. Next class, we'll talk about what do we do with our wave functions. All right, have a good one, guys.
I accomplished much in my 2048 game.
Yeah.